Hello, and welcome to applications of stoichiometry to thermochemistry, specifically to using delta H. All right, so we're going to look at this first problem here. These are in the thermo practice number 6. So we have a reaction here. We are also given the delta H value, and it says determine the amount of heat energy generated when 6 moles of H2O reacts with excess NH3. There's a trick to solving this problem where we come up into the problem and we say, okay, well, we're going to say that one reaction, Rxn, equals one reaction, and then this is equal, sorry. Okay, one reaction equals NH2 plus 3H2O. And the reason why we're doing this is this per mole over here, this per 1 mole, is per 1 mole of the non-substance, per 1 mole of reaction. It's delta H of reaction. And this basically just gives us a 1 mole ratio to compare to, okay? So we are going to say, okay, well, if there's 6 moles of H2, so we're going to start with 6 moles H2, because that's the given. And we're going to have to use our intrinsic property, that's right here. The problem is this is in moles of reaction, not moles of H2. So what we can say is, okay, well, there are 3 moles of H2 for every 1 mole of reaction, right? Because every reaction equals this up here, okay? So then we can say, okay, well, now we're out of moles of this, and we can actually use the moles of reactions. Per reaction, you get negative 92 kilojoules per 1 mole of reaction. So then it just works like normal stoichiometry. And then you would just put this into the calculator, and you would get negative 184 kilojoules. Now it's not per mole because moles cancels out, and that's how much energy. You could then use this, plug this into MCAT, and actually get temperature readings. All right, so this is the same reaction, different problem. In order to form 300 milliliters of NH3 at 1.5 atm, 23 degrees C, how much heat energy is released? The reason why it's released is because this is an exothermic reaction. It's negative. Okay, so obviously we are going to come in here. We're going to write our reaction equals Rx and equals. So that gives us that 1 mole stoichiometry, right? So it's 1 mole of reaction equals this. But we can't do anything right now because there's no moles. So how are we going to get to moles? This is a gas. We can use Pivnert. So RT, that'll get us to moles. Now that'll give us to moles of NH3, and we can use stoichiometry to get to the reaction. So we have 1.05. Volume is 0.3 because we have to convert it into liters. N is what we're solving for. This is 0.0821. Temperature is 23 plus 273, which is 296. And so we'll put this into the calculator, 1.05 times 0.3 divided by parentheses 0.0821 times 296, close parentheses, and we get N equals 0.012. Actually, it's going to be 30 when we round. Moles, and this is moles of NH3. So now we can take this and we can say, okay, we have 0.130 mole NH3, but we can't compare that to this value yet because that's in moles of reaction, not in moles of NH3. Mole NH3 times, okay, well, there are 2 moles NH3 for 1 mole of reaction. Now we're in moles of reaction, and there is negative 92 kilojoules per 1 mole of reaction. Now it's just a matter of dividing by 2 times like 92, and we get negative 0.596 kilojoules, or, because this is energy released, right? So it's negative. You're giving off heat energy, or you could do 596 joules if you want to convert it back and make sure that negative sign is still there. Okay. So there's some additional practice problems. In the next practice problems, your delta H is not negative, it's actually positive. And the only thing that really changes is instead of releasing heat energy, that's going to need heat energy in order to either use up the reactants or to form the products.